Hi everyone. So we will see some more problems based on concept of electrostats. So you can see this question. 2-point charges of value minus 20 microcoulomb and 20 microcoulomb are placed on the x-axis at x equal to minus 10 centimeter and x equal to plus 10 centimeter respectively. Calculate the potential and electric fields at the points P and Q. Coordinates of P as well as Q it is given. Find the work done in carrying a unit positive charge from the point O to Q along a straight line joining P and Q, as well as is there any path along which the work done is less than the above value. So one by one we will discuss this question. So 2-point charges of value minus 20 microcoulomb and plus 20 microcoulomb. So minus 20 microcoulomb and plus 20 microcoulomb. So here suppose this minus 20 microcoulomb and here you have this plus 20 microcoulomb. This is located at A and that coordinate is given as minus 10 centimeter. So if O is the origin, so from here this will be minus 10, y coordinate of this it will be 0. Similarly, x coordinate of this it is given as 10 and again y coordinate 0 because they are along the x-axis. Here it is already mentioned, it is along the x-axis. So it is minus, so we have to calculate it at this point Q, which coordinate it is given as 20, 0. Now, so one by one we will be calculating. So potential and electric field at the point P. So let us first calculate it at the point P. So here charge is here and charge is here. So suppose if you can consider this point is P, we have this charge Q1 here and we have this charge Q2 here. Potential at the point this P. So if this distance is suppose R1 and this is R2. So potential at P due to Q1, that will be how much? Q1 upon 4 pi epsilon naught R1. Q upon 4 pi epsilon naught R, that is the general relation for the potential as far as the point charges are concerned. So we can calculate this potential. Similarly, potential due to this at this point, that will be Q2 upon 4 pi epsilon naught R2, but here it is given as R1 is equal to R2, so that we can replace. So total potential due to these two charges Q1 and Q2 at the point P, it will be what? Potential due to this plus potential due to this, just because potential it is a scalar quantity, so we don't have to bother about its vector addition or vector subtraction. So here this will be a simple case of addition. But when we calculate potential, so here there is no problem as far as the direction is concerned because it is a scalar quantity. But we will calculate the potential at the point P with the proper charge sign here. If it is suppose negative, so we will consider minus of Q1 upon 4 pi epsilon naught R1. If it is positive, we will consider plus Q2 upon 4 pi epsilon naught this R2 in general. Okay, then we will replace R1 is equal to R2 provided they are same. But second part of this is we have to calculate the electric field. Electric field, that means the electric intensity or electric field strength. So here if it is suppose minus, so let us say Q1 is minus and Q2 is plus. So electric field, it is a vector quantity. So depending on this minus sign and plus sign, we will have to first check the direction of the electric field. So now the point where we are considering the electric field or the electric potential, a unit positive charge is supposed to be present there. So when we calculate here, it means we are considering this potential or the electric field for this unit positive charge. It means here the charge is positive in nature, here charge is negative. So there will be force of attraction. Electric field, it is also a force per charge, that is termed as your electric field. F it is equal to Q into E or F by Q it is equal to E. So that relation we have. So positive here, negative here. So that electric field here, if it is suppose E1, so E1 it will be acting this side. Here Q2 is positive and this is also unit positive charge. So it means E2 it will be in this direction. So E2 it will be this side, E1 it will be this side. Again E1 and E2 they are vector quantity because that is nothing but the force, electric field. So we, using the vector sum, we will calculate the resultant of this E1 as well as this E2. Once we have decided the direction, this E1 and E2, is this clear? Due to this minus Q1 and plus Q1. So here the significance of minus and plus is that decides the direction of the electric field. So because of this minus sign, we can consider that this will be this side. Because of this plus sign, we could consider that this. Now once you put it, the value in the numerical expression, in that case now we will not put the minus sign or the plus sign, both will be considered with the positive sign even if it is the negative charge. So here a magnitude of the intensity, that is E1, due to this charge Q1, it will be Q1 upon 4 pi epsilon naught R1 square. Now we will not consider minus Q1 upon 4 pi epsilon naught R square, because already the direction has already been taken due to the presence of this negative sign. So it is simply Q1 upon 4 pi epsilon naught R1 square. Due to this, it will be Q2 upon 4 pi epsilon naught R2 square in this direction, just because of its positive. In case of potential, what we have observed, potential, it is a scalar quantity, so there is no problem as far as the addition, vector addition is concerned. But when we calculate potential, so we will calculate it due to this negative charge, so minus of Q1 upon 4 pi epsilon naught R1 plus Q2 upon this 4 pi epsilon naught R2, and then we will have the simple algebraic sum of those two quantities. Here we will not have the simple algebraic calculation, because intensity, it is a vector quantity, but this minus and plus sign, that will already decide in which direction these electric fields will act, and accordingly we can calculate the resultant of these two vectors. Or if there are suppose more number of charges, there will be more electric intensity, so the resultant of all those electric field or electric intensity. So that way we will calculate it. So here, so if we consider, so already this distance, it is known to us, this distance is known to us because these coordinates are known to us. This is minus 10 and this is plus 10. So this total, it will be equal to how much? 20. 10 and 10, that will be 20. Now coordinate, so all these coordinates we can calculate. So this is 20, this is 10, this is 10. So we can calculate the value of R1. Okay. Similarly, we can calculate the value of R2, because R1 and R2, that will be same, because this side and this side, it is same. Angle APB, angle, this is your point A, this is P and this is B. So angle APB, this angle, that is equal to how much? 90 degree. This angle, it will be equal to 90 degree. It means that triangle is right angle at this point. Q2, it is given 20 microcoulomb. Okay. So, and Q1, it is given as 20 microcoulomb. So this is, and these two charges are same in magnitude but opposite in direction. So we have this Q1, we have this Q2, point coordinates are known to us. So we have to calculate electric field and intensity at this point as well as at this point. So let us now calculate it. So potential at the point P. So potential at point P, it will be due to Q1 as well as due to Q2. So Q1 upon 4 pi epsilon naught R1, Q2 upon 4 pi epsilon naught R2. R1 is equal to R2, that we have already mentioned in the diagram. So substituting the value, you can calculate it. Now see this, without calculation also we could have said, as far as the potential is concerned, because this is the symmetrical point with respect to this charge as well as this. This distance is 10, this is also 10, and this is in the mid of this entire region. So and magnitude of the charge here and charge here, it is same. So obviously magnitude is same but signs are opposite. Here it is minus, here it is plus. So when we add them, and distances are also same, so obviously potential due to this, it will be cancelled by this, or vice versa, potential due to this charge, it will be cancelled by this, and that's why we are getting. So without calculation we could have used this concept that it is simply a algebraic addition. One is with the minus sign, another is with the plus sign, magnitude of both it is same. So obviously when we add those plus and minus, they will cancel each other and it will become 0. So substituting the values here, you can see, So either you can substitute and then you can calculate it is 0, or just using the concept of symmetry as well as magnitude of charges, we can say that the potential it is 0. Now calculate the intensity. So E1 that will be equal to how much? Q upon 4 pi epsilon naught R1 square. That R1 we have this. This is your Q1, this is Q2, and here we have to calculate it at point. This we have assumed R1. So Q1 upon 4 pi epsilon naught R square. This in which direction? This direction, because this is negative and here there is unit positive charge. Q2, similarly we can calculate this E2. So E2 it will be how much? Q2 upon 4 pi epsilon naught R2 square. R2 and R1 it is same, Q1 and Q2 in magnitude it is same. So we can replace it and we will get this relation. This is in which direction? This is along this line. Okay, because that will be repulsive in nature and this is attractive in nature, because this is minus in sign, this is plus in sign. Now E1 and E2 are at right angle to each other, because this is 90 degree, this angle is 90 degree, so obviously this will also be 90 degree, because this total is 180 degree, this total is 180, this is 90, so obviously this is 90 degree. Now two forces are acting at right angle, so what will be the resultant? F1 square plus F2 square square root. Here it is E1 square plus E2 square square root. So that you can calculate it. So this gives you the resultant of these two EMFs, these two electric field, this as well as this. Okay, this side we have this E1 and this side we have this E2. This angle is 90 degree. So resultant of these two, it will be this square plus this square square root. Simplifying, we can calculate this. Now the resultant of this, so obviously when it is 90 degree and in magnitude E1 and E2 are same, so tan theta is always y component upon x component. So either you can simplify that way, or you can consider from symmetry that this and this it is same, both are at 90 degrees, so obviously it will be it will be along which line, which is bisecting this, so this will be along this line, so resultant it will be along this and this, so resultant it will be along this, and that will pass at an angle of 45 degree either from this line or from this line. So that's why it say is parallel to x-axis, because this line it will be parallel to this x-axis. Okay, directed from B to A. This is your A here and this is B here, B to A, this side, because one is along this line, another is along this line, this electric field, so resultant will be along this line, not along that line. So from this B to A along x-axis or with respect to this line or this line at an angle of 45 degree. That again, without calculation we are able to conclude this, just because magnitude of E1 and E2 it is same, angle between these two it is 90 degree, so obviously the line will pass bisecting these two lines, so it is at 45 degree or 45 degree. Now see the second part. Second part we have to calculate potential and intensity again at the point Q. So again at the point you can see this again. We have to find the potential at the point P and Q. So again here this is along x-axis. So x coordinate it is given as 20 centimeter, y coordinate 0, it means the point P is lying along x-axis. So point Q is lying along x. So we have to calculate it at this point. So again due to this charge, here it is minus, here it is plus, and plus how much? Unit positive charge. Wherever we have to calculate potential or intensity, at that point a test charge is supposed to be present, and that test charge means unit positive charge. So unit positive charge. So again this will be what? Attraction. It will try to attract it, and this charge it will try to repel it. So again the resultant it will be what? This minus this or this minus this, depending on which one is more, which force is more, this side force or this side force, or this side intensity or that side intensity. So from here coordinate or this distance it will be how much? 20 centimeter this is 10, this is 10, and this is 20. So from this point it is 20. So from this point it will be 20 up plus this 10, that is 30. So distance of this point from this point it is 30, and distance of this point from this point it will be this, which is equal to 20 from here. So from here it will be 10. So from this charge it is at 10, from this charge it is at a distance of 30. So using this relation we will be able to calculate it. So let us now calculate. So now we can see potential. We have to now calculate potential at the point Q. So when we calculate potential at the point Q, so we have to calculate potential due to the charge Q1 as well as potential due to charge Q2. So already we have seen that the distance from the point A, it was how much? 30, and from point B it was 10. So it is 1 upon 4 pi epsilon naught Q1 upon AQ plus 1 upon 4 pi epsilon naught Q2 upon BQ. Now putting the values of these constants, that is 1 upon 4 pi epsilon naught, that becomes your 9 into 10 to the power 9, Q1 upon this plus Q2 upon this. Now when we are calculating potential, so we are putting the value of charge with the proper sign. So here this is negative, so you have this minus sign, here it is positive, so we have that plus sign. Now after simplifying you will get this value. Now just to calculate the electric field here at the point due to charge at point A and similarly due to charge at point B. So again we will consider Q1 upon AQ square, and 1 upon 4 pi epsilon naught Q1 upon AQ square. Here it is 1 upon 4 pi epsilon naught Q2 upon BQ square. Now again AQ and BQ both are known to us. Substitute the values and that we can calculate this as well as this. Now this is from Q to A, from Q to A. So here if you recall this diagram, so here we have this A, this is your B, and this is the point Q. Now this is negative in nature, here charge is positive, so this will attract. So here even it will be in this side, and this will be force of repulsion plus and plus, so it will be this side. So both these electric field, due to charge A it is this side, due to charge B it is this side, and this will try to attract it and this will try to repel it. So it means both are in the two opposite direction but along the same line. So electric field, resultant electric field, it will be how much? Either this minus this or this minus this, depending on the magnitude of their electric fields. So here, so once we calculated this E1 dash as well as E2 dash, now E1 dash and E2 dash are in opposite direction, that we can see here, and they are along the same line. So directly we can consider the resultant field, it will be this minus this. Simplifying, we are getting this value. So directed from B to Q, directed from B to Q means in this direction. It means this E2 it is, or E2 dash, it is more than this E1 dash. So final or the resultant direction, it is along the line BQ, from B towards that Q. So this way we can calculate it. The third part of the question, if you see, third part of the question say, is there any path along which the work done is less than the above value? The work done is less than, work done is what? The potential difference as far as the unit positive charge is concerned, and that potential difference becomes work done when Q amount of charge is replaced from one position to the another position. So that we have to just see. Now work done from this Q to P, so Q into VQ minus VP, Q charge into potential difference between the points P and Q. Substituting, we are getting 1.2 into 10 to the power 6 joule. Now the third part of the question says, is there any other point? Okay, the work done in moving a charge between 2 points in electric field depends only on the potential of the end points. Work done is W is equal to how much? W it is equal to Q into potential difference. It only depends on the potential difference. Okay, depends only on the potential of the end points and is independent of the path followed between the points. Therefore, it is always the same, because work done, this is the scalar quantity. This only depends on the potential difference between the 2 points. So suppose you have this point 1 and you have this point 2. Either you approach this way, or you approach this way, or you approach this way, or you approach this way. The length of the path does not matter. It is only the potential difference between the 2 points. So we have to calculate potential at this point and this point, whether you are taking this path or this path or this path. That is not the concern. So potential at this point and this point. So whatever path we chose, potential at this point and this point, that remains same. Potential difference remains same. So work done will always remain same. So that's what this says. It is the independent of the path followed between the point. Therefore, it is always the same, because Q, that is the charge. Potential difference does not depend on this. It is just depending on the potential at two particular points. From there we get the potential difference, and from that we calculate the work done. I hope this is clear. Now let us come to the next question. So see this question. This question says that the electric strength of air is about this 3 into 10 power 6 Newton per coulomb. The electric field strength, electric field, it is nothing but the force. That's why here we have this Newton per coulomb. By this we mean that if the electric field exceeds this value, sparking will occur. What is the largest charge a 0.5 centimeter radius metal sphere can hold if sparking is not to occur in the air surrounding it? Now, outside the sphere, all the charge on the surface acts as if it is located at the center. Suppose you have a sphere, you have this is uniformly charged. Okay, throughout every point there is the charge. Now, it is uniformly charged as far as this surface is concerned, but it is supposed to be concentrated at the center of this spherical sphere, center of the sphere. This is supposed to be considered. The behavior of these charges are such that it is supposed to be located at the center of the sphere. Now from this concept, we can say the intensity at a distance r from the center, it will be how much? 1 upon 4 pi epsilon naught q upon r square. Putting r is equal to this. What is this? 5 into this. What is the largest charge? A 0.5 centimeter radius. 0.5 centimeter radius. This is the radius. So it means all these charges are supposed to be concentrated here. Okay. Now intensity at any point on the surface, that will be kq upon r square. Intensity at any point on the surface of this sphere. So it is kq upon r square, because the charge which is spread across this sphere is supposed to be concentrated, or its effect is felt such that it is supposed to be located at the center of this. So taking this location, any point on the surface, it is at a distance of r, so that gives you the intensity as q upon r square, means kq upon r square. So substituting this, and electric field strength, because this is the maximum value. If sparking does not occur, it means we can take up to what? The maximum value. Beyond that, if you take, then the sparking will happen. So that we don't have to consider, because what is the largest charge corresponding to this metal sphere of this much of radius? So largest charge value, it means we are maximizing the electric field strength which it can tolerate or it can bear, and that we are taking 3 into 10 to the power 6. Substituting these values, we are calculating charge 8.34 nanocoulomb. That is q is equal to 8.34 nanocoulomb. So it means if this much of amount of charge is placed over this sphere, which has a radius of 0.5 centimeter, then sparking will not happen, because this will produce intensity up to this maximum level, which is 3 into 10 power 6 Newton per coulomb. This is the maximum level. So any charge less than that, it will have less intensity, and when less intensity means there will be no sparking. So that's what this problem demands. Now let us see this question. Find the electric field at the center of a uniformly charged semicircular arc, that is at the point P as shown in the figure. So this is your semicircular arc. Okay, charge is uniformly distributed over this. We have to calculate the electric field at this point. We have to calculate electric field at this point. Now see, due to point charge or due to concentrated charge, if a charge is concentrated at this point, let us say it is Q, which we say a point charge or a concentrated charge at any particular point, at a distance of point P, we have intensity how much? KQ upon R square. This is because of the point charge or concentrated charge. But here, charge is uniformly distributed throughout the surface. It is not concentrated here, here or any particular point. It is throughout distributed over this uniform circular arc. Because of this presence of this charge, we have to calculate the intensity at this point P. So just to simplify this, what we will do is this uniformly charged, which is distributed across this surface, we will change it to a point charge or a concentrated charge, that is concentrated at any particular point or at any particular small area. So once we consider that, then we can directly use the Coulomb's law. Okay, Coulomb's law, because this relation we get from the Coulomb's law only, and that is for the point charge KQ upon R square. Using that, we will be able to elaborate and we will be able to move forward. So let us see how it happens. So here, if you assume the charge per unit length is L, charge per unit length, because charge is uniformly distributed, so charge per unit length we are taking lambda, and the radius of the arc to be A. Radius of this, it is suppose A. Splitting the arc into a small segment delta S. Delta S, suppose you take this delta S, any small parts. Each part it is equal to suppose delta S. Okay, so here we can now consider, we have this radius A, suppose you take this delta S, okay, this is small element as delta S, this much we are taking delta S. We have the essentially point charge on each will be how much? Lambda delta S. Per unit length it is lambda, charge per unit length it is lambda, so for delta S length charge will be how much? Lambda delta S. Okay, either you write this way or if you take this, so lambda delta S. The way you assume, just multiply it here. Charge per unit length is lambda, so lambda for unit length, lambda for twice of that, that will be 2 lambda, 3 lambda. Similarly for ds length or delta S length, it will be lambda into ds. Okay, now for this small elemental charge, either this or this, now we can use the Coulomb's law, because this becomes your point charge or a concentrated charge or a small elemental charge. A small elemental charge, and only this much part we are taking. Now if we consider this lambda ds of charge over this surface, lambda ds of charge, let us say just for our simplicity, suppose it is equal to q dash. Lambda ds, let us say it is q dash, because ds is a very small segment, so that charge it can be considered as a concentrated charge or a point charge, so let us say it is q dash. Now because of this q dash, force at this point, so force at this point or electric field at this point, it will be in which direction? This direction. Okay, force it will be in this direction, because unit positive charge is supposed to be concentrated here when you calculate the intensity or potential. Positive charge is uniformly distributed across this, so this is plus in nature, this is also plus in nature, so there will be force of repulsion. So intensity it will be in this direction. Now if we take this angle as theta, then we can resolute this intensity. One component will be this side, another component will be this side as well as this side. Similar element, symmetrically we can consider this side, just similar to this, and small delta S this side also. So for this, again the intensity will be what? This side. Due to this charge, it will be this side. Due to this charge, it will be this side. Symmetrical to this we are considering. When I say symmetrical, this angle theta, so here also we are taking this small element at an angle of theta. Why we are taking? Just because if it is producing intensity this side, so similar to that there will be a surface, because here it is uniform distribution throughout the surface, there will be a surface which will produce intensity in this direction. Now component of this, again it will be this side as well as this side. Now you can see one of the component of this, it is along this line, one of the component along this line, they are along the same line but in the two opposite direction. Intensity, magnitude of this intensity and this intensity, it will be same, because this distance as well as this distance is same, charge across this and this it is same, so both parameters are same, which is responsible for intensity. So magnitude of intensity here and here it will be same. Now if you observe the component, one of the component of this, it is this side, another component is this side. They are same in magnitude but opposite in direction, so they will cancel each other. It means the net intensity at this point only depends on this vertical component. Horizontal components are cancelling each other, so it only depends on the vertical component. This is clear? So now once it depends only on the vertical component, we will take this vertical component or calculate this and we will proceed with this. This can be avoided, because every element, if you take element here corresponding to that here, so horizontal component of this, it will cancel. Similarly, if you take element here and corresponding to this here, so again horizontal component of this and horizontal component of this, it will get cancelled. Only the vertical components will remain. Summation of that or integration of that will give us the total intensity at this point due to this entire charge which is spread across this uniform semicircular arc. So it means we will be interested only in the vertical component. Why we are interested only in the vertical component, I hope this is clear, because for every element, this side and this side, from the symmetry, we found that horizontal components are cancelling each other, only the vertical components are adding as far as the electric intensity at this point is concerned. So let us calculate this. So that you can see delta S here. So intensity will be this side. This angle we are taking theta from geometry. This will also be theta. Here it is delta EY, taking this Y axis and this as X axis. These components are not there just because we have just discussed that they will be cancelling each other. So delta EI, it will be equal to how much? 1 upon 4 pi epsilon naught delta SI upon A square, because this distance is your A. So Q upon R square, Q here it is lambda delta S, R here it is A, Q upon R square, so it is Q upon R square. This is your constant K, that is 1 upon 4 pi epsilon naught. Now we have, now here if you find this, we have already discussed why X component will be cancelling each other, only the Y component will be responsible for intensity at this point. So if we calculate the Y component, so this becomes lambda upon 4 pi epsilon this delta SI cos theta, because this component is theta, sorry, this angle is theta, so its component along this direction will be how much? E cos theta. This side it will be E sin theta, here also E sin theta. This component, these components cancel each other, only this remains, so we have this cos theta. Now from this side and this side we need to integrate. Either you take this theta varying from this angle to this angle, or we can take it from what? 0 to pi by 2, but twice of that, because the integration limit it will be from minus pi by 2 to plus pi by 2. Either you take integration limit from minus pi by 2 to plus pi by 2, or you put this factor 2 here. And why this factor 2 here, that I hope you understood, because here there is Y component from this side and Y component from this side, so that this was responsible for the intensity at this point. X component, they were cancelling each other. So if you consider from this side and together this 2, then we have to take this theta from 0 to pi by 2, only this part. And if we don't take this factor 2, then theta, it should vary from what? From this point to this point, that is from minus pi by 2 to plus pi by 2. So you can see this here. Now, so we can see this integration limit, lambda cos theta. We have not taken this 2 here. Directly we have used from minus pi by 2 to plus pi by 2. So after simplifying this, we will be able to calculate this intensity. So lambda upon 4 pi epsilon naught a sine theta minus pi by 2, because integration of cos theta, that becomes your sine theta minus pi by 2 to plus pi by 2. Simplifying sine pi by 2, sine minus pi by 2, these things are known to us. Substituting the value, you are getting lambda upon 2 pi epsilon naught. Integration, and here if you take suppose 0 to pi by 2, then you have to consider this factor, because here if you say minus a to a f of x dx, this is same as your twice of 0 to a f of x dx. These are the properties of the definite integration. Minus a to a f of x dx equal to twice of 0 to a f of x dx, provided f of x is an even function. And if it is odd function, then it will become 0 after this integration. Now here you can see that it was an even function, because this side, if you take this element, so this side also we are taking this element. So symmetry is maintained. Symmetry is maintained, and that's why we can use this. Either mathematically you can bring this factor 2 when you integrate it, or during the integration only you can define the limit of theta. If you take 0 to pi by 2, it should be twice of lambda, twice of this lambda upon 4 pi epsilon naught cos theta 0 to pi by 2. Or if you take the entire limit from minus pi by 2 to pi by plus pi by 2, it means you are taking either this side or this side, then theta will vary from minus pi by 2 to plus pi by 2. In that case, we will take only this lambda upon 4 pi epsilon naught. So considering either this or that, you will get the similar relation, and that becomes your lambda upon 2 pi epsilon naught. This you can also keep in mind as a standard relation, that due to circular uniformly distributed charge over a semicircular arc, the total intensity at the center, it becomes lambda upon 2 pi epsilon naught a, where a is the radius of that semicircular arc and lambda is the charge per unit length. So charge per unit length, as we were discussing. So wherever necessary, you can directly use this relation, or if you want, you can derive and then you can substitute it. So now we can see the next question. So here we have, find the electric field at the center of a uniformly charged semicircular arc, that is at point P in the figure shown, if the charge distribution lambda along the arc is non-uniform and is given by lambda is equal to lambda naught sine theta. Now with theta measured as shown in the figure. So here this is our theta. We have this point P. Now in the previous example, we have seen that lambda is uniformly distributed. Lambda is uniformly distributed throughout the semicircular arc, but here it is non-uniform, because lambda depends on this angle theta. Lambda depends on this angle theta. So because of that, lambda is also non-uniform, and it is distributed across this surface of the semicircular arc. So now we have to calculate this electric field at the point P. So again, as we have discussed in the previous example, you can see the y component at point P, it will be what? 0. The y component is 0, since the charge distribution is anti-symmetric, means that is not symmetric. In the previous example, if you recall it, so we had taken, if this is point P, we have taken this small element this side and this side. So intensity due to this and this, it is same, because this angle is theta and this is theta. So corresponding to this, if we can take suppose this element, similarly this element, all are symmetrical. But here, as the charge is non-uniformly distributed, so charge charge across this small element, it will be different from charge across this small element, even though this angle is theta and this angle is theta, or alpha and alpha. So it is non-symmetric. So because of that, y component, it will be 0 at the point P. Now for the incremental x component, we have delta Ex, that will be lambda upon 4 pi epsilon naught a square, because a is its radius. So lambda upon this 4 pi epsilon naught a square delta sine theta, because charge, it will be equal to how much? Lambda delta s, lambda delta s. So that will be equal to your lambda this sine theta, because we are taking this x component here. This is your lambda here, lambda delta s in general, but we are taking at an angle of theta. So at an angle of theta, so component will be how much? Lambda delta s sine theta. But again this lambda, it will be replaced by what? Lambda naught sine theta. So lambda naught sine theta, so it becomes your lambda naught sine square theta. Sine theta into sine theta, that becomes sine square theta. This lambda naught sine theta, so that lambda naught will be taken out of this integration, sine theta, that makes it sine square theta. Again, as we have taken the integration from minus pi by 2 to plus pi by 2, so here also theta will vary from this point to this point, so that is from minus pi by 2. So we have this delta at an angle of theta. Charge here, it will be lambda delta s. Okay, now the x component of this, if this angle is theta, so this component, it will be how much? Sine theta. If this this angle would have been taken as theta, then this component would have been cos theta. So here we have taken this as theta, so this becomes your sine theta. The component, it is sine theta, that's why we have this sine theta here. Lambda ds is the small elemental charge across this small element. Now we can't take it from this side, because here charge is non-uniform, so that's why the integration, it is directly from minus pi by 2 to plus pi by 2. We have this sine square theta, integrate this sine square theta, substitute the value, and you will get this relation. Now why this minus sign? That we have already discussed, because minus of lambda delta Ex, this negative sign only implies that it simply gives us the direction, whether we are taking point along the electric lines of forces or against the electric lines of forces. On the basis of that, we have these signs. Now integrate and you will get lambda upon 8 pi epsilon naught. If you recall the previous example, so here it was lambda upon 2 pi epsilon naught, lambda upon 2 pi epsilon naught. Now in this case, because this charge is also variable, so it is coming as lambda upon 8 pi epsilon naught a. So this way we can calculate. It means the logic is whether it is uniform, non-uniform. The logic here is what? We will take a small element, okay? We will calculate this charge across this, because once it is a small element, so that will behave as a point charge. Once it starts behaving as point charge, the Coulomb's law in its form, it starts working. Using that, we will come across this expression for the intensity. Now there will be certain variable quantities. Considering that, we will have that integration limit based on the variable quantity which is being integrated. Simplify and you will get the intensity. So now see this question. A long thin rod is bent into a circle of radius b. So this is the thin rod, okay, and it is bent across this circle of radius this b. It is uniformly charged along its length. Throughout it is uniformly charged. Find the electric field at the center of the field. So we have to find electric field at the center of the circle. Radius, it is given as b. Now when we bend it and when we get the circle, so obviously this charge here, it will be distributed throughout this circular surface. This is uniformly distributed. Now if you take a small element this side and symmetrical to this small element this side, or a small element this side and a small element this side, intensity, they will what? They will cancel each other, because due to this small elemental charge at this point, and again I will remind you, whenever we calculate the intensity or potential at any particular point, a unit positive charge is supposed to be located at that particular point. So here again this unit positive charge, here this is plus, so intensity it will be in this direction. Due to this small elemental charge, intensity will be this. They are symmetrical to each other, so that will be that intensity, it will be along the same line. So these two will cancel each other. Similarly, intensity due to this and this, it will cancel each other. Similarly, intensity due to this and this opposite, it will cancel this. It means, so this is for the small element. Now again you can consider for semicircular arc, this part intensity will be this side, and for this part intensity will be finally this side. So again this intensity and this intensity, they will cancel each other. So what will be the final intensity at the center? It is 0, because they are cancelling out each other. So it is 0 just by symmetry. So there is nothing to calculate. You can use the concept of symmetry and then we can calculate. Due to semicircular arc where the charge was uniformly distributed, intensity it was lambda upon 2 pi epsilon naught A. So due to this part, this side intensity it is lambda upon 2 pi epsilon naught A. Due to this semicircular arc, it will be this side lambda upon 2 pi epsilon naught A. These two will cancel each other. So finally intensity at the center, it will be 0. Now consider this question. A rod lies along the x-axis. Now suppose we have this x-axis and this is your y-axis. A rod is lying along this. Okay. A rod lies along x-axis with one end at the origin. So this end is at the origin and the other at x equal to infinity. So this goes up to infinity. It carries a uniform charge lambda coulomb per meter. So again there is uniform charge lambda coulomb per meter. Okay. Starting from Coulomb's law, find the electric field at the point x equal to A. So this is origins, obviously x equal to A this side. So x is equal to minus A. So this is A here on the x-axis. So starting from Coulomb's law, we have to find the electric field at this point due to this uniformly charged rod which is lying along x-axis. One is end at the origin, another extend up to infinity. So now again we will take a small element, suppose this dx at a distance of x. This is small element, suppose this dx, this is small element of this rod at a distance of x from the origin. Now we have to calculate intensity here. So from this small element, this point will be at a distance of how much? This is x, this is A, so it is x plus A. Charge across this, it will be how much? Lambda dx. So you can consider lambda into dx. Distance is A plus x, that you can consider. So r square, so A plus x whole square. Constant 1 upon 4 pi epsilon naught, so 4 pi epsilon naught. Now this x here, now just see the limit. X we have assumed distance of this small element from the origin. So this x here from where? 0 to infinity. Don't get confused, we have to take it from here because we have measured or we have taken this small element from origin. So x is varying, not this distance. X is varying and that is from 0 to infinity. That's why we will have the integral limit from 0 to infinity dx upon A plus x whole square. Simplify this, it is a simple integration. You can consider A plus x to the power minus 2. A plus x is linear, so you can just use the relation for x to the power n dx, integration of that, simplifying, putting the values this 0 and infinity, you will get this. So it is lambda upon 4 pi, lambda upon 4 pi epsilon naught A. This is 4 pi. Lambda upon 4 pi epsilon naught A. 4 pi epsilon naught A. So this is your intensity due to this rod at this point. Now again you can see this question. A rod lies along the x-axis. This rod lies along this x-axis, okay, with one end at the origin. One end at the origin, and the other again extending up to infinity. So this goes up to infinity. It carries a uniform charge, again lambda coulomb per meter. Starting from Coulomb's law, find the electric field Ex and Ey for the point on the y-axis where y is equal to b. So we have to consider, suppose a point, let us say we have to consider this point which is at a distance of b from this. So we have to calculate the electric field at this point and their x component as well as the y component. Okay, so let us calculate. So here again dE, and if you consider this small element again here, this is small element, this is again taken, always these are the standard assumption. Consider a small element at some distance from the origin or any particular point, and then consider a small charge across that, use the Coulomb's law, and then again have the variation of this. Once it is a case of variable, so instead of addition or summation, we will use the concept of integration. So here again, charge across this, it will be how much? Lambda dx. So we have this lambda dx. Now this point is taken at a distance of r from here. So obviously this will be 4 pi epsilon naught r square. So q upon this r square, that becomes your intensity, and this intensity due to this point in this direction. Okay, it will be in this direction. So this is the intensity. Now this r. So we will consider the variation of r. Before doing that, we may need the resolution along x axis as well as the y axis. So dEy, that will be how much? dE cos theta, because this angle is theta, this angle is theta. So this component it will be what? Cos theta. This is your dE. If you assume this theta, it means this theta, using the concept of geometry. So this is dE, this is theta, so this component it will be dE cos theta, and this component it will be how much? dE sin theta. So x component it will be dE sin theta. This is your x component here, and this is y component here. This is y component and this is x component. So x component it will be dE sin theta, and y component it will be dE cos theta. Now x is equal to how much? B tan theta, because this distance is theta, this is b, this is theta, and this is your x. So using the concept of the triangle, right angle triangle, we can calculate all these components. So x is equal to b tan theta. These things are known to us. So dx, differentiating that, we will get what? Differentiation of tan theta is sec square theta. So dx equal to sec square theta d theta, or dx upon d theta is equal to sec square theta. Now r is equal to how much? B upon cos theta. Again this is b, this is theta, this is r. So again we can calculate relation between r and b, and that we find r is equal to b upon cos theta. So now you can replace dx, we can replace in terms of what? Sec square theta d theta. This r we can replace in terms of b upon cos theta. Just substitute it, so that y component it becomes what? Lambda b sec square theta d theta upon 4 pi epsilon naught b square sec square theta into cos theta. Y component here it is dE cos theta. So this is your dE. Okay, so and this cos theta means this cos theta. I hope this is clear. We have this dE expression. Now we have dEx expression, dEy expression, means resolution of this dY along y axis as well as x axis. We have calculated x in terms of b and theta. Differentiating, we got this dx in terms of theta. Why it is done? It is not necessary that I should consider this. You could have moved like this, but in that case it is your choice which variable you want to keep, and accordingly you will put the integration limit. Either you can consider this x in terms of theta, then we will have the limit of this x, or you can consider theta in terms of x, then we will have the limit of that theta. So it means it is just the change of variable depending on which will be convenient for us to use. So that's what we have considered. So x equal to b tan theta. Now we are trying to replace this x in terms of theta. So dx equal to sec square theta d theta. So that has been replaced here. Y component we have cos theta. So we have cos theta. Okay. So now, so after simplifying, we are getting this Ey, any y component of that field, integrating from 0 to pi by 2 as far as the variation of that theta is concerned, and simplifying we are getting lambda upon 4 pi epsilon naught b. Similarly, you can calculate this x component of that electric field, and again simplifying and integrating sin theta from 0 to pi by 2, you will get this lambda upon 4 pi epsilon b, and here also it is lambda upon 4 pi epsilon naught b. Now, if the rod were infinite in both the direction, the answer would obviously become Ex equal to 0 and Ey is equal to. So, Ex will be how much? Ex, x component. If it is infinite both the sides, and it from the rod moves from minus infinity to plus infinity. So, obviously this point will become what? For this rod, this point will become symmetrical. Intensity due to this side and this side, they will cancel each other, because intensity due to this side of the small element, it will be this side and this side. Y component of this, it will be this side. Y component of this, it will be this side. X component of this, it is this side, and X component, it is this side. So they will cancel each other. So X component, it will become 0, and only Y component will remain. That's why X component is 0 and Y component. So this is for the infinitely long rod, which is symmetrically placed with respect to the origin. So it extends from minus infinity to plus infinity. So if the rod is of infinite length, extend from minus infinity to plus infinity, then at any point on the y-axis, intensity along x-axis, it will be 0, and we will simply have the y component of the intensity. Why it is there? I hope you have understood it. Thank you.